This is your presenter Asloob Mudassar, and I am presenting slide number 126 of the course on laser physics. Question is: transient behavior of a CW continuous wave laser when it is switched on is oscillatory, which immediately leads to stable behavior after oscillations known as relaxation oscillations, discussed in question number 125 or in slide number 125. The continuous operation of the laser still shows pulsating behavior, which is due to some instability known as dynamic instability. Discuss dynamic instabilities and pulsating behavior of a CW laser during its continuous operation. The answer is: it has been observed that a laser system operating in a CW mode exhibits continuous pulsating behavior, which most of the time is irregular and sometimes regular. The output beam has an average value and contains irregularly spaced pulses or spikes with randomly distributed amplitudes. The output behavior is due to some kind of instabilities, which may be referred to as dynamic instability, and is the main cause of pulsation in lasers. Typical output behavior from a CW laser operation is shown in figure 126.1. So let me show you that figure first. So this is the caption is typical intensity output behavior from a CW laser operation. So you see that the intensity I of t is plotted vertically, and here I have the time which is plotted horizontally, and you can see that the behavior that the behavior is pulsating, that is not uniform, that is the intensity is not constant purely, but you see that the intensity is fluctuating, and sometimes you can see that there are pulses over there, and these pulses are actually randomly spaced and randomly occurring with random amplitudes, and the time is in microsecond. So this is the plot up to 100 microsecond, starting from nearly 15 microsecond and onward up to 175 microseconds. So this is the behavior after switching on the laser. In a single mode laser, so you see that here we are particularly talking about the single longitudinal mode. That is, the laser is operating at only a single frequency. In a single mode laser, fluctuations in the pumping process or in the cavity losses is responsible for intensity noise. So you see that here you can see fluctuations in pumping process or in the or the fluctuations in the cavity losses is responsible for intensity noise. If these factors are randomly modulated, it will lead to a noise in the laser output intensity. If the factors or the laser parameters are sinusoidally modulated, then the output intensity time behavior can be described using rate equations by incorporating modulation of appropriate parameters. So you see that here we are talking about what? Laser parameters are sinusoidally modulated. So here we are talking about that if the laser parameters are sinusoidally modulated, then the time intensity behavior can be described using rate equations by incorporating modulation of appropriate parameters. So you see that here we have to incorporate modulation parameters, appropriate modulation parameters that can modulate the parameters of the laser system. Here we are talking about the pumping mechanism. For example, in this case, for pump modulation, the pump rate Rp can be described as Rpo, that is the pump rate at initial time t is equal to 0, and we are now including some variations in some modulations in pumping rate, that is delta Rp multiplied by e to the power iota omega t. And this R of P, you can assume that this is the pump rate when the stability, when the steady state operations is obtained. So this RPO is the pump rate at a steady state operation. So you see that after you see that here I have talked about some behavior. For example, here in the question you can see relaxation oscillations. When you switch on the laser, then you see that there are some oscillations which are randomly oscillations, and the intensity of the laser randomly fluctuates or oscillates, and you see that after some time these relaxation oscillations vanish out and the laser becomes stable. That stability, so when the laser achieves stability initially, then you see that the pump rate is referred to as the RPO. That is the pump rate at the steady state operation. So RO, this O stands for the steady state operation, and RPO is the stands for the pump rate at steady state operation. And here we are adding, you see that some modulation in the pump rate, which is delta RP, that is a small fluctuations in the pump rate multiplied by e to the power iota omega t, where omega is the frequency of the pumping mechanism. And you see that here pumping mechanism means that another laser is being used to pump some other lasers, and the pumping laser has a frequency which we say that it is operating at a frequency omega. So here you see that we are imposing one condition, that the variation in the pump rate is much smaller than the pump rate at a steady state value, that is RPO. So delta RP is much less than RPO. And you know that this is steady state value, the pump rate at the steady state value. And here we are considering that delta RP, that is the magnitude of the pump rate, is much smaller in comparison with the pump rate at the steady state operation. The pump modulation modulates the inversion and the number of photons present in the cavity. So you see that in the previous slide we have discussed this statement in much greater detail, that the inversion and the number of photons are responsible, and the number of photons in the cavity, when they fluctuate, then of course this will causes a fluctuation in the output intensity of the laser output beam. So here the pump modulation modulates the inversion, that is the population inversion is being modulated by the pump rate, and the number of photons present in the cavity are also will also fluctuate with the pump rate. So that is, we can say that n of t, that is the inversion as a function of time, is equal to n naught plus delta n naught as a function of time multiplied by e to the power iota omega t, where n naught is the population present at the steady state condition. So n naught is the population at the steady state condition. And you see that when there are no disturbance, the laser will have the population and will retain its population inversion at the value n naught, which we call the steady state inversion. But if we assume that the population inversion undergoes some variation, then we include this term, that is delta n naught as a function of time, that is the variation in the inversion will change as a function of time also, and then we are multiplying with some modulating factor, which is e to the power iota omega t, and this modulating factor is due to the modulation of the pump beam. So n of t is equal to the population, so population inversion at any time t after the laser has obtained the steady state operation, and even if there are some variations in the inversion, then we can say that the inversion as a function of time is equal to the inversion at the steady state value plus the variation in the amplitude of inversions, that is delta n naught as a function of time multiplied by the fluctuations which are governed by this factor e to the power iota omega t, where omega is the frequency of the pumping mechanism, that is the pump beam which is being used as a pumping source, has a frequency operating at omega. Similarly, we can say that the number of photons will also fluctuate with the pump modulation. So we can say that phi of t, that is the number of photons at any time t, is equal to phi naught, that is the number of photons at steady state value. Phi naught is the number of photons at the steady state value plus delta phi naught as a function of time. This delta phi naught as a function of time is actually the variation in the number of photons with the time after the steady state operation has been obtained, and then multiplied by e to the power iota omega t, which I have already explained while talking about the explanation of the inversion as a function of time. So you see that inversion will change with time, and of course the number of photons will also fluctuate with the time, and this is what I have given. But you know that there are some conditions on delta n naught and delta phi naught. That is the magnitude of delta n naught, that is the variation in the population inversion. Delta n naught is much smaller than the population inversion at the steady state value, which is n naught. And similarly, the number of photons after the steady state condition will be much smaller than the original number of photons present at the steady state condition. So delta n naught is much less than n naught. Similarly, delta phi naught is much less than phi naught. The rate equations which we have discussed in set number 1, that is in equation number in equation question 125.1 and equation number in question number 125.2. These two equations form set number 1, and similarly for the set 2, which includes these two equations, that is equation number 3 and equation number 4 from slide number 125, become linearized. So you see that these two equations, that these two set of equations, that is equation 1 and 2, and the other set of equations, that is equation number 3 and equation number 4, these two set of equations become linearized under these conditions. That is delta n naught is much less than n naught, and similarly delta phi naught is much less than phi naught. And you know that the first set of equations given by equation number 1 and 2 were applicable to the 4-level laser system, and equation number 3 and equation number 4 were applicable to the 3-level laser system. And for the detail of these, you can consult previous slide, that is slide number 125. And you know that there, in order to linearize those equations, we used these two conditions. But you know that while discussing the previous equations in the previous slides, we didn't have this function, that is e to the power iota omega t, was not present in both of these equations which we have included, because here we want to include the modulation, pump modulation, that what is the effect of a pump modulation in the fluctuations of the laser output beam. So the single mode laser, here still we are talking about a single mode laser, that is the laser is operating at a single longitudinal mode. The single mode laser then operates at its natural resonance frequency omega r. This omega r is the output of the laser beam, which is operating at a single frequency nu r, or in terms of the angular frequency omega r, after settling of relaxation oscillations. So you see that when we switch on the laser initially, relaxation oscillations take some time to settle out. So after a few microseconds, then you see that we obtained the steady state conditions, but the steady state conditions are still modulated due to the modulation in the population inversion of the system, modulation in the population inversion of the system, and the modulation in the number of photons. Due to these variations, the laser beam can still show some instability, and this is what we are going to discuss, that one. So here, that is why we have talked about, that is the single mode laser operation, which operates at its natural resonance frequency omega r after settling of the relaxation oscillation. Now the pump modulation at frequency omega. This omega is the frequency of the pump beam, and this omega r is the frequency of the output laser beam. So the pump modulation at frequency omega, you see that in the previous equation, that is in these two equations we have discussed, we have multiplied delta n naught and delta phi naught by a factor e to the power iota omega t, because this factor, that is the population, is being modulated by this factor, which is due to the pump beam, which is due to the frequency of the pump beam, which is omega is the frequency of the pump beam. So here we can say that the pump modulation at frequency omega is responsible for the modulation of laser frequency omega r. The amplitude of laser oscillations is maximum when omega, becomes equal to omega r. That is when the pumping frequency of the laser beam becomes equal to the frequency of the laser which is being pumped. So when omega, that is the frequency of the pump beam, matches with the resonance frequency of the output laser beam, then of course the amplitude, that is the amplitude of laser oscillations, is maximum. If the pump is non-monochromatic, that is the pump beam contains many frequencies, for example, and has a white spectrum. White spectrum means that all frequencies are almost have the same magnitude. All frequencies are present, and such a beam is called, that is the beam has a white spectrum. Then the intensity noise spectrum of the output beam will be broadband, peaking at omega r. So if you notice the spectrum of such a laser beam, that is the output intensity of such a laser beam will have a noisy spectrum, and you see that the noisy spectrum will peak at the resonance frequency omega r of the output laser beam. But you see that there some other frequencies can also be present over here, and we will be talking about that is the intensity noise spectrum will be broadband, peaking at omega r. That is the peak will occur only at this resonance frequency of the laser, but you see that some other frequencies will also be present, making the overall spectrum broadband. Now here we are talking about something a little bit about dynamic instability. So the dynamic instability means that the instability which occurs with the continuation of time, that is with the existence of time. That is, as the time goes on, then the instability will persist there in the oscillations of the laser beam. So that's why it's called a dynamic instability. So the dynamic instability in a single mode laser leading to a pulsating behavior is also possible, but under special conditions. So you see that if our laser is operating at a single longitudinal mode, then we can still talk about that some dynamic instability could be possible in such a laser which is operating at a single mode. But you see that under special conditions only. And what are those special conditions which we are going to discuss over here? For example, a homogeneously broadened laser at nu c, where nu c is you know that if you multiply with it 2 pi nu c, that becomes omega c. That is a frequency. Omega c is the frequency of the laser which is operating, but not at its central frequency. So omega c could be a frequency which is away from its central resonance frequency. So for example, a homogeneously broadened laser which have a central frequency nu naught, but the laser, for example, is operating at nu c with delta nu c, that is the line width corresponding to that frequency is a delta nu c. So if delta nu c is greater than, much greater than delta nu naught, operated well above the threshold, and the laser also operating well above the threshold value, then you see that such a laser can also exhibit pulsating behavior. So let me again tell you that, for example, a homogeneously broadened laser at operating at nu c, having a line width delta nu c much greater than delta nu naught, where delta nu naught is the line width when the laser will operate at a frequency nu naught, that is the central frequency in the gain profile is nu naught, and the delta nu naught is the corresponding line width. So when the laser is operating at a frequency nu naught, having a line width delta nu c much greater than the line width of the laser when it will operate at a frequency nu naught, which is delta nu naught. So for example, a homogeneously broadened laser at nu c with the delta nu c much greater than delta nu naught, operated well above the threshold, can exhibit pulsating behavior. So the second condition is that here we are imposing two conditions on a single mode laser to show the dynamic stability, and the two conditions are that one condition is that a laser is operating at a frequency which is not the central frequency of the gain profile, but this is a frequency lying either to the left of the center of the gain profile or to the right of the gain profile, having a line width delta nu c which is much broader, which is much greater than the delta nu naught. This is one condition, and the second condition that the laser is operating at a threshold at a value which is much above the threshold value. So under that condition, under these two conditions, even a single mode laser can show the dynamic stability. Now we are talking about multi-mode laser. So pump modulation in a multi-mode laser is responsible for switching the laser between the modes or between the set of modes, resulting in dynamic stability. So you see that when we are talking about multi-mode laser, in which already many longitudinal modes are operating, then due to the pumping modulation, due to the modulation in the pumping mechanism, what will happen? The laser will switch into different frequencies. That is the peak frequency at which the laser will switch will one of the many frequencies contained in the multi-mode laser. So the switching of a frequency will take place in the output beam due to the pumping modulation, and this is responsible for the switching the laser beam between for switching the laser between the modes or between the set of modes, resulting in dynamic instability. And due to, since different longitudinal modes in the multi-mode laser will have different amplitudes, so when the laser will switch onto different modes very quickly, very randomly with the pump modulation, then due to the variation in the amplitude of those multi-mode frequencies, then of course the dynamic stability in the output of the beam will appear. The dynamic instability in a multimodal laser may be associated with the anti-phase motion among the oscillating modes. And the main reason is that in the laser, you see that many modes are operating in the laser cavity. Some modes are operating from, for example, at one time, if some modes are operating from left to right, then at the same time, some modes will also be operating from right to left, and you see that their phases will be different from each other. So due to different phases of the oscillating and multi-mode frequencies within the laser, they will be in anti-phase with each other, and due to the anti-phase motion among different longitudinal modes within a multi-mode laser, then of course what will happen, the fluctuation, the dynamic instability will occur, because the cancellation of these anti-phase motion will also cancel out some of will attenuate the modes corresponding to some of the multi-mode lasers, and will enhance where the phase will matches, the amplitude will be enhanced. So you see that the dynamic instability in a multimodal laser will be very evident, but dynamic instability for a single mode laser will be special under these two special conditions which we have discussed. So you see that even after the laser is operating at a steady state value, after the steady state value, even you will see that after, for example, the steady state values are obtained after maybe in a couple of microseconds. For example, maybe within 20 microseconds, you have obtained the steady state value, and this is the picture of the fluctuations in the intensity of the beam after the steady state operation. So even you will see that after the steady state operation, the laser intensity also fluctuating, and you can see the randomly occurring peaks located at a different position in time, which are random in time, and the amplitude of these peaks, you will notice they are also random. And this is after the steady state operation of the laser, and this is due to two main reasons that we have explained, due to the modulation, due to the modulation in the due to the variation in the in the inversion of the laser beam, that is in the population inversion, which is varying with the time, and due to the number of photons which are also varying with the time, and due to this variation, the laser fluctuation will also fluctuate with the as the number of photons will fluctuate in the laser cavity. And this is the main reason for this fluctuation, is the fluctuation in the pump modulation beam. So this is the end of slide number 126.